In this section of the video, we're going to cover the last engineering applications of integral, which is the moments and center of mass. We're going to also talk about the centroid of a plane and the theorem of Pappus. So the purpose of finding the center of mass is to find a point P on which a thin plate of any given shapes balances horizontally. So if you're given any thin plate, you want to find out a point where the plate balance basically. So this point is called the center of mass or center of gravity of the plate. So imagine if you have two masses, two particles with the mass m1 and m2 attached to a rod of negligible mass on opposite sides of a fulcrum at the distance d1 and d2. So you know that the rod will only balance if m1 times d1 equal to m2 times d2. So this is the basis. How do we find the center of mass of several particle systems? So let's convert the physical system into a mathematical form so that we can solve the problem mathematically. So instead of the particles lying on the rod, so suppose that the rod lies along the x-axis, so with m1 at the point x1 and m2 at the point x2, and the center of mass is at x bar. Okay, this is the center of mass. So let's compare this system with the previous figure where the length d1 is this distance. So d1 equal to x bar minus x1, and here is the length d2. Okay, so this is the length d2. d2 equals to x2 minus x bar. Thus, to find the center of mass, the system will only balance if m1 times d1 equals to m2 times d2. So d1 is x bar minus x1 and d2 is x2 minus d bar. Okay, so you just substitute and rearrange and find out that put x bar as the subject of the equation, and you get that the coordinate of x bar is equal to m1 times x1 plus m2 times x2 over the total mass m1 plus m2. So here m1 x1 and m2 x2 are called the moments of the masses m1 and m2 with respect to the origin. So our origin is here. Okay, the distance. So the origin is when we start to measure the distance. So okay. So previously you were given only two particles, m1 and m2, and the locations of m1 and m2 are at x1 and x2. But what if you have more than two particles? So in general, we need a general expression for a system where you have n number of particles. So let's say you have a system with n number of particles with mass of each particles m1, m2, m3, and so on until mn, located at each points x1, x2, x3, and so on until xn on the x-axis. Then you can find the coordinate, the x coordinate of the center of mass by adding all the moments divided by the total mass of each particle. Okay, so you got this. And now if we let m to be equal to the summation of the mass, and the big M here, capital M, to be the summation of the moments. So we can simplify this formula into this. Okay, so basically if we put this and this, we get x bar equal to M over M, where M is this and the big M here is this. So rewrite this in terms of this equal to mx bar equals to m. So what this means, and then additionally the sum of individual moments capital M is also called the moment of the system about the origin. Okay, just m here is just the total mass. Okay, you just add m1, m2, m3 until mn. But when you add the summation of the product of mass times the distance, you will get the moment of the system, the whole system about the origin. And if you want to find the x-coordinate of the center of mass, so you divide by the moments of the system by the total mass of the particles in the system. Now let's consider a system of n particles with masses m1, m2, and until mn. So in this example, it's just 3 particles, but you can have more than that, more than 3 particles. So let's say each of the particles have their own respective coordinates at points x1 and y1, x2, y2, and x3, y3, and so on until xn and yn in the xy plane. By analogy, with the one-dimensional case, we define the moment of the system about the y-axis to be this one. Okay, so previously you just have a rod and the mass. Okay, that's why it is the one-dimensional system just now. Okay, so you have this x bar. Okay, sorry, there's a renovation in the office, so that's why it's a bit noisy, so just please bear with it. Okay, so M1 and M2, and let's say you have other masses and so on until Mn. So you just have to calculate the distance and then you get the moment, and it's a one-dimensional system. But in this case, you have a two-dimensional system where you have an xy plane. So you have several particles in xy plane at various coordinates. So you need to define the moment of the system about which axis, about y-axis and about the x-axis. So here you have both. Okay, my is defined as the moment of the system about the y-axis. So it is the summation of the product of mass and the distance from the y-axis. Okay, so if you look at this graph here, so this is your y-axis. So the distance of m1 from the y-axis is given by x1. The distance of m2 from the y-axis is given by x2, and so on. M3, the distance from the y-axis is this long, x3. So the moment about the y-axis is equal to the product of each mass times the distance, i.e. the x-coordinate. So my measures the tendency of the system to rotate about the y-axis. And also there is a moment of the system about the x-axis. So about the x-axis, you have to measure the distance of the particle from the x-axis. So for m1, with coordinate x1 and y1, so the distance of particle m1 from the x-axis is given by y1. M2, the distance is y2. M3, the distance is y3. Thus, mx, the moment of the system about the x-axis, is given by the product of each mass times the distance from the x-axis respectively, which is the y-coordinate. So mx measures the tendency of the system to rotate about the x-axis. This leads to, let us find the coordinates, x and y coordinates of the center of mass in terms of the moments by the formula, these formulas. Okay, so to find the x coordinate is equal to my over m, and to find the y coordinate equal to mx over m. The center of mass x, y, coordinate x and y here is the point where a single particle of mass m would have the same moments as the whole system. Okay, let's do example 5 for moments and center of mass. So find the moments and center of mass of the system of objects that have masses 3, 4, and 8 respectively at the points -1, 1, 2, -1, 3, 2 respectively. So you can illustrate your system. So these numbers 3, 4, and 8 are the mass of each particle. And a coordinate for mass with 3 is -1, 1, so you put it here. For 4 is 2, -1, and for this one, the 8 here is 3 and 2. Okay, so to find the moments and center of mass, the solution, you first calculate the moments about x and y axis from the formula mx and my, and then you calculate the coordinate for the center of mass from this formula. Okay, let's do it. So find mx equals to summation from I equals to 1 to I equals to n, mi, no, sorry, it's y, okay, yi. So in this case, m1 times y1 plus m2 times y2 plus m3 times y3. So that will give you 3 times negative 1 plus 4 times 2 plus 8 times 3. That gives you 29. And find my, summation of from I equals to 1 to I equals to n, mi xi. So you get m1 x1 plus m2 x2 plus m3 x3. So 3 times 1 plus 4 times negative 1 plus 8 times 2 gives you 15, and the total mass equal to m1 plus, just add everything together. 3 plus 4 plus 8 equals to 15. So the x coordinate is my over m, 29 over 15, and yeah, just leave it there. And the y coordinate is mx over m, 15 over 15, 1. So the center of mass is 29 over 15 and 1. So you can put it back into the graph to just see where this coordinate is located. So we talk about finding the center of mass for a system of particles in the xy plane. What about the center of mass of a flat plate or a lamina that occupies the region R on a plane? So the center of mass of the plate is called the centroid of R. Okay, so we use the symmetry principle. Let's say if R is symmetric about a line L, then the centroid of R lies on the line L. Okay, for example, let's say if you have a rectangle as the lamina. Okay, so you have a rectangle. So what is the centroid of the rectangle? So then we can do a symmetric division of this rectangle. So okay, symmetric about that vertically and symmetric about here horizontally. So it is symmetric on this line L, and it is also symmetric about this line L. So the centroid of the rectangle must lie on both lines. So that centroid must be here because this point is the point where it lies on both line L. Okay. Same thing with the region R here. So this region R here is not just like rectangle, it can be defined in all sorts of function, curve. Okay, next we define the moments such that if the entire mass of a region is concentrated at the center of mass, the moments will remain unchanged. Now suppose that the region R lies between the lines x equal to A and x equal to B. So the intervals is A to B above the x-axis and beneath the graph of f, where f is a continuous function of x, okay, f of x. So what we do is we divide the interval A and B into n subintervals with equal width delta x. So we start with here A as x0, and then x1, x2, and so on until xn. So we have this a sample point here. So let's take this sample point xi minus 1 and xi. So in the middle of xi minus 1 and xi is lies the xi bar. Okay, so let's just not confuse things and just put xi bar here. So let x bar equal to the average between xi minus 1 and xi. So it's just xi minus 1 plus xi divided by 2. Then you got this x bar here. The centroid of the i's approximating rectangle, so this rectangle here, you can call it Ri. Okay, so this is let's say this is R1, R2, R3 until the i's rectangle, you call it Ri. So the centroid of Ri is the center of the rectangle. Okay, so the center of rectangle, the coordinate of the center of the rectangle is xi bar, and the coordinate for the center would be half of the function of fxi, right? This is the y coordinate of the y coordinate of the centroid for rectangle Ri, and then the area of Ri is just the area of a rectangle where its length times the width. So the length, the height of the rectangle Ri is fxi bar, and the width is delta x. So since this is a lamina, a thin lamina, there's no volume, it's just area, the mass of the lamina is given by rho times the area, the density times the area. So that area is given by f of xi bar times delta x. So this we got the mass. So because when we want to find the centroid, just like we want to find the center of mass, we need to have something in terms of mass. Wait, before we proceed, so let's have a look at the different regions. So just now we talked about the region Ri. So what about the region R1, R2, R3, and so on until Rn at the end of this lamina? So okay, just to visualize with you where the centroid of this curve will lie on the graph. Okay, so if you have this R1 here, you approximate the central to be this one, and the center is here, and the center is here. You know, as the rectangle grow higher than the central, I mean, yeah, if you know what I mean, the center of the rectangle, just find the center of the rectangle, and then the centroid of the lamina must lie on this line L. Okay, the centroid must lie on this line because the centroid of each rectangle lie on the respective points where it's the I bar. Okay, so for example, this is R1, then you have this one is X1 bar, X2 bar, X3 bar, and so on and so on. So you just have something in the middle of each rectangle. Thus the centroid must lie somewhere on that line. Just now we mentioned the mass of the rectangle is given by the density times the area. So density rho times the area, fxi bar times delta x. Now we want to find the moment of Ri about the y-axis and then x-axis. So first let's find out the moment about the y-axis for the rectangle Ri would be the mass times the distance from the y-axis, i.e. the xi. So the mass is just rho times fxi bar times delta x, and then the distance of that particular point is xi bar. Then you can just simplify this, fxi bar delta x. So this is the moment about the y-axis for the rectangular Ri. So when we want to find the moments for the whole line, so you add these moments and obtain the polygonal approximation to R by taking the limit as n approaches infinity. So my for the whole region R would be taking a limit as n approaches infinity, add all the moments of Ri together, you know, from R1, R2, R3, and so on until R equals to n. So start from I equals to 1 until I equals to n, rho xi bar f xi bar times delta x, and convert this into integral form. So you take out the rho because it will be constant, and since we divide the interval from a to b, then just fx dx. Okay, so this is the approximation to find the moment about the y-axis. Similarly, we can do the same to find the moment about the x-axis. So m of x for the region Ri is the mass times the distance from the x-axis, i.e. the distance given by the half of the fx. Okay, so remember for the region Ri, so this is your xi bar, so this is your center of the rectangle, and this is given by half. So until here is fxi, but until this point only is half of fxi bar. So then mass is same like what we have before, density times area delta x, but now the distance would be 1/2 function of fxi. Then you simplify this into rho 1/2 times fxi squared delta x. Did I miss anything? No. Okay, then similarly, so since this is for Ri only, and we are finding the moment from R0 to Rn, so for mx of the whole region R, we take a limit as n approaches infinity. Yes, summation from I equals to 1, and then write down everything again. Okay, then convert it in terms of integral from a to b. Yeah, you can take out the density because it's constant, and then you have 1/2 fx only, but this whole thing here is squared dx. So this would be the formula to get the moment of r about the x-axis. Compare that with the one about the y-axis. Okay, but we are not done yet, because in order to find the x and y coordinates for the centroid, we need to have the total mass, right? So x bar is my/m, and y bar is mx/m. So just like the system of particles, the center of mass is defined such as this. So we follow the mass of the plate now is m equal to rho times a, which is rho times the density is the density times the area. So area is just the area under the graph of fx dx from a to b. So x bar is my/m. So the my is just now we obtain rho times the integral from a to b x fx dx, and divide by m. M is rho ab fx dx. Okay, so you can slash out the density here, but you please don't slash out the fx dx here, because of it doesn't work that way. Okay, so you end up with the integral from a to b x fx dx divided by the integral from a to b fx dx. So that's the x coordinate for the centroid, and for the y coordinate, follow what we have derived just now. You got mx equals to rho times integral from a to b half of fx squared dx divided by the mass ab fx dx. So y is just, you just can eliminate the rho but not the integrals. Okay. So that will give you the y coordinate of the centroid. So you can see that the density is cancelled in both locations, both points coordinates. So meaning that the location of the center of mass is independent of the density. Okay, so in summary, you can write the center of mass of the plate also in terms of A. So x bar here equal to 1/a ab x fx dx, because this whole thing here is equals to a, right? This a. Similarly for this one also, equals to 1 y over a, ab 1 over 2 fx squared dx. Okay, so that was how you can find out the centroid of a lamina if you are given the region R, and then it's just between the region R and the x-axis. But let's say if the region R now lies between the two curves, fx and gx. So how do we find the centroid of a lamina? So fx is greater than gx. Okay, so fx is at the top and gx is at the bottom. The centroid can be found in following the similar argument. So you just adapt this fx and gx into the previous formula. So previously your x bar is just equal to 1 over a integral between a and b x fx dx previously. But when you have two functions and the region is trapped between the two functions, so you just take fx minus gx to get only the inside of this curve. Similarly, for the y coordinate, 1 over a, the integral from a to b, half. Previously, you just have fx squared dx, but now, since you have these two, you just minus lah, okay? Fx squared minus gx squared, and follow the limit a to b. That's all. Okay, to conclude the applications of integral into engineering stuff, let's relate the centroid of a plane with the volume of revolution, and this is given by the Theorem of Pappus, where he says that if R is a plane region that lies entirely on one side of a line L in the plane, and if R is rotated about the line L, then the volume of the resulting solid is the product of the area A of R, of the region R, and the distance d traveled by the centroid of R. If you want to know more about the Theorem of Pappus, you can watch the YouTube video given in the QR code, or you can type the link, because this professor, he provides a more detailed information on the Theorem of Pappus and its conception and application. So feel free to watch the video, and in our next example we will show the application of Theorem of Pappus. So in this example we will use the Theorem of Pappus to find the volume of a torus. So what is a torus? A torus is formed by rotating a circle of radius r about a line in the plane of the circle, that is a distance r, where r here is bigger than the lowercase r, from the center of the circle. Find the volume of the torus. So you can imagine this situation as illustrated in this figure here. So this is the center of the circle. So you have a circle with the radius r here. Okay, this is your circle. So this circle travels at the distance capital R from the center of this graph of this plane. So it travels round and it forms a torus. So this circle travels on the plane and it forms a torus. So basically it's like a donut. Okay. So to find the volume of torus using the Theorem of Pappus. So Theorem of Pappus say that the volume of the torus is equal to the area times the distance traveled. So this circle here has the area of A equals to pi r squared. By the symmetry principle, its centroid is its center. And so the distance traveled by the centroid during the rotation is, the distance is equal to d equals to 2 pi r. It's just the circumference of the circle, the bigger circle. Okay. Therefore, by the Theorem of Pappus, the volume of the torus is the area times the distance traveled. The area is 2 pi r. The distance is 2 pi r, and the area is pi r squared. Thus, you get this value of the volume of the torus formed. You can substitute the value of r squared and r with any numbers that you are given. Okay, that's the end of our lecture for this week on the engineering applications of integration or integrals. But these are just some examples. Okay, you don't, I mean, the main takeaway here is actually for you not to memorize how to get to the derivation of the formula or function, but rather for you to conceptualize how to use integration when you are given an actual engineering problem. Okay, these are just examples. There are many other examples of engineering applications out there. You will see them in your later years of your life in the course, especially when you go to third year in modeling, then you will use more of it. Okay, so thank you all for your attention, and see you when I see you.